we're going to discuss hypothesis testing, which is in many ways really simple, but as statisticians, we find ways to make it more complicated. The techniques can seem odd and confusing, but the most important part that I want you to take away from this is that actual hypothesis testing is pretty straightforward. The complications come from the formalism that we put on top of it. Those complications are necessary. I don't want to say they're not, they're not unnecessary or pointless. Hypothesis testing is very powerful. Some of the power comes from that kind of stilted, unnatural sense. They're genuinely interesting questions that people ask all the time. One example, I heard students in the hallway, one asking the other a question, well, if there's nothing going on between you, then why is she on your phone so much? That's a basic sort of hypothesis test question right there. If there's nothing there, then why do we observe these things that we observe? One of the basic questions of the hypothesis test is, how likely is it that I'm being fooled? That I'm imagining there's some pattern there when there's actually not truly there? We know we've all been fooled by seeing patterns in randomness. People are into astrology because they believe that some random patterns of stars in the sky have influence on their life. As scientists, we understand that actually the stars are just randomly scattered in what looks like patterns. But our little ape brains from millions of years of evolution have gotten good at trying to see patterns in the world, even when there's nothing actually there. It's easy for us to be fooled, so we start by asking, well, what would I expect to see if there were nothing there? If there were really no pattern, just randomness? If conventional wisdom were true, or if there's really no difference, that's the null hypothesis. We ponder the question, what would I see if the null hypothesis were true? In the example we did in lab, the experiment asked you to mess around with dice and try to modify them to get the 6 come up more often. The null hypothesis is that the dice is fair. Each side has equal probability coming up. We all know that in real life I might roll a dice and get 6 on the first time. That's 1 in 6 chance. I can roll the dice twice in a row and get 6 both times. I can figure out there's a 1 in 36 chance of that. It's not impossible. It's not even very unlikely. We could certainly see it if we're playing a game where players roll the dice many times. To start to formalize the hypothesis testing, I'd want to get a sense of, if I roll the dice 20 times, how many times might a 6 come up? Even if the dice were completely fair. If conventional wisdom were true, if nothing had been done to these dice to alter them, that's what we call the null hypothesis, H0. We contrast that with the alternative hypothesis, HA. The likelihood that I'm going to be fooled is the p-value. Later we'll talk about problems of people putting too much faith in p-values. But the idea is valid, even if sometimes overdone. Before we look at the evidence, we start with the question, how low does the p-value have to be for me to reject the null hypothesis? How much evidence do I need to make a decision? There are a lot of details. We don't actually accept the alternative hypothesis. Either we do not reject or we reject the null hypothesis. It's the difference between saying, okay, the null hypothesis looks false, there might be some kind of pattern, versus saying, and I know what the pattern is. It's intuitive to understand why we would ask, how much evidence do I need in order to make a decision? To decide, I'm not being fooled, there's really something there. By convention, and really nothing more, but in so many studies in social science, we use 5%, sometimes 1%. That gives a boundary. So if the p-value is less than 5%, people would typically say we reject the null hypothesis. Then if the p-value is greater than 5%, we'd say we do not reject the null hypothesis. Again, not the same thing as saying we accept the null hypothesis. It may be, and in fact often is the case, there's some evidence against the null hypothesis, but I'm not 95% certain that I'm not being fooled. I'm not very confident that the null hypothesis is wrong. We can often end up in these borderline cases. There's some evidence, but it's not really strong. Sometimes that may be that there's just not enough data. If I'm running an experiment, I can do the experiment again, or I can wait until I get some more data. There are plenty of cases where people say, I can't be sure yet. Let's take a normal example. Normal. Often we form a hypothesis test about a mean. Although we can test any value for the mean without loss of generality, we'll often test against the null hypothesis that the mean is 0. Commonly, the null hypothesis is, well, there's nothing there. We would say the null hypothesis is that the mean is 0, h naught is that the value mu equals 0, versus HA, the alternative hypothesis, mu is not 0. Recognize we're comparing two very different hypotheses there. The null hypothesis is focused on a point. Mu is exactly precisely equal to 0. Whereas the alternative is mu is something else. I don't know what else. Could be anything. Any real number. Those are very different kind of hypothesis, which should remind you of why we're not saying we accept one or the other. We might be able to reject the claim that mu is 0, but even if it's not 0, we might not have a good answer for what it actually is. Anyway, when we look at a sample average under the null hypothesis, the sample average is typically distributed normally. There are cases where it's not, but those are weird. The central limit theorem tells us that under pretty broad conditions, the sample mean is going to have a normal distribution, mean mu, standard error, that we can estimate from the data. Under the null hypothesis, the mean would have a normal distribution. Note for small samples, we have to correct for the fact that we're estimating the standard error. We'll come back to that later. Talk about the t-distribution. For now, take it as a decent approximation. The sample average is going to have our usual bell-shaped normal distribution around the true value under the null hypothesis. That's part of why the normal distribution is called normal, because it's so common. If I divide my estimate of the mean, x bar, by its standard error, then that ratio is going to have a standard normal distribution. Under the null hypothesis, it's going to have a mean of 0 and a standard error of 1. Suppose I calculate x bar over the standard error to be 1. I can then ask, is that a big difference? Is that a big number? In the null hypothesis formulation, we say that if the true value of mu were actually 0, what is the probability we could observe a value of 1 or farther from 0? So in the little picture on top, what's the probability we're in that purple area, the bell-shaped graph, not the middle? In calculating these areas, we find the p-value, because the p-value is going to be that purple area. That's the probability that I could observe a value as extreme as, or even farther, from 0. That's how we calculate the p-value. We calculate the area under the curve, and that's why it's very important for statisticians to learn how to do that. It's one of the basic things that we do again and again. We can set different levels of the test, but a common version would say we reject the null hypothesis of mu equals 0 at the 5% level if the p-value is less than 5%. We can look at the area and say that is the same as, once I calculate x bar of the standard error, if that's greater in absolute value than 1.96, then I'm going to reject the null hypothesis that mu is 0. Or do not reject if this ratio x bar over the standard error is less than 1.96 in absolute value. Which is the same rule as do not reject if x bar is between minus 1.96 and positive 1.96 times the standard error. We often approximate that to twice the standard error because 1.96 is awful close to 2 and can do the mental arithmetic a little bit easier. That gives us a confidence interval. If the null hypothesis is true, then I'd expect to see certain values of x bar, and if that confidence interval includes 0, then I would not reject the null hypothesis. If the confidence interval does not include 0, then I could reject the null hypothesis. The p-value is the smallest probability that would still reject the null, so you can also calculate that. For example, if somebody reports a p-value of 4% for some particular estimation, maybe I'd say, okay, that's less than 5, I would reject. Now again, don't take all this, without any complications and subtleties. We'll keep on getting back to those throughout the course. But this is the simple version.